everyone, I'm Jessica, and this is Luke.
Welcome back to our channel. In this episode, we're going to talk about batteries and motors for EVs. But before you hit the back button and watch that AI-generated video where old Stallone meets young Stallone, we promise that you might learn some interesting facts about why the electric car has been in the making since the early 1800s. Yep, that's right, the 1800s. Before the advent of the gasoline engine, and for those with overworked horses, early carriages were originally powered by electric batteries. Around the 1830s, inventors in Europe and the United States were experimenting with battery-powered carriages, and one of the earliest practical electric vehicles was built by a Scottish inventor named Robert Anderson. These were crude versions of what we see today and used a single zinc acid battery, unlike the 12-volt rechargeable lead acid batteries that are yet to be developed. Once rechargeable batteries were developed, the options for recharging or replacing them were still limited, and these electric carriages were mostly only available to higher income families. Consider that the electric grid was also developing, and many homes didn't even have electricity back then. With the progression of the oil drilling industry during the mid-19th century, which was mostly aimed at providing kerosene for lighting, and the then discarded byproduct gasoline found a new purpose, providing a cheap and efficient fuel for internal combustion engines. This changed the landscape for battery-powered vehicles, but over the next few decades, despite their impractical batteries, electric vehicles were still competitive. In 1890, William Morrison, another Scot who settled in Iowa, built a 6-passenger electric wagon in the United States. It wasn't fast, but neither were the roads at the time, and speed limits were really not a thing. By the early 1900s, electric cars were thriving. The Standard Electric Car Company made an automobile that used Westinghouse electric motors and claimed to have a range of 110 miles on a full charge. In a 1913 newspaper ad, it was claimed that it was the only electric in America built and sold for less than $2,000. EVs were clean, quiet, and easy to operate, no hand cranking required. Gasoline cars, on the other hand, demanded a more robust frame to handle those tiny little explosive reactions inside each cylinder. Electric vehicles accounted for roughly a third of all cars on American roads. Brands like Baker Motor Vehicle Company and Detroit Electric catered to urban drivers who valued reliability and a smoke-free commute. With the introduction of Henry Ford's Model T in 1908, which was a mass-production made gasoline car, made far cheaper than electrics. A few years later, Charles Kettering, a prolific American inventor, engineer, and businessman, invented the electric starter, which made gasoline cars even easier to operate. Much cheaper and capable of longer ranges thanks to abundant fuel and an expanding road infrastructure. It's interesting to consider that much like our current limited electrical charging infrastructure, the first gasoline cars were fueled by buying gasoline in cans from pharmacies, hardware stores, and blacksmith shops. Early drivers would purchase fuel, often known as cleaning solvent, also known as Ligroin, and pour it into their vehicles using a funnel, a slow and hazardous process. Meanwhile, electric cars struggled with limited battery technology and shorter range. By the 1930s, they had largely vanished from mainstream production, and it seemed like the age of the electric car was over like a flash of lightning. Speeding forward about 50 years, we began to see the electric vehicle making its comeback. Environmental concerns, along with urban air pollution and oil dependency, governments were motivated to seek a better way to reduce emissions with the ever-growing number of cars and trucks on the roads around the globe. The 1990 Zero Emission Vehicle (ZEV) mandate, introduced by the California Air Resource Board, required automakers to begin developing vehicles with zero emissions. In response to this mandate, several experimental cars appeared during the 1990s. The most famous was General Motors' EV1, introduced by the General Motor Company in 1996. It had an impressive technology for its time, including aerodynamic design and advanced battery systems. However, it was only leased to drivers and was eventually discontinued in the early 2000s. The true commercial comeback came with hybrid vehicles, which combine an electric motor with a gasoline engine. For most, like the popular Toyota Prius released in 1997 in Japan, they utilize a drive system that was powered by both a small internal combustion engine and a high-voltage AC motor. It became the first mass-production hybrid vehicle and arrived in North America in 2000, and quickly became a symbol of fuel efficiency and environmentally conscious driving. Technically speaking, in 1999, the Honda Insight was actually the first hybrid sold in the United States, although the Prius became far more popular. We actually had a Gen 2 Prius ourselves for many years, and so this has also helped us give us some insight into the inner workings of an electric-powered vehicle. Without an electric charging infrastructure, hybrids succeeded because they solved the biggest limitation of the early EVs, which was range. Drivers could benefit from electrical efficiency without having to worry about running out of battery power. This is where we get into how we chose our batteries.
Up until the late 2000s, battery technology was still somewhat limited to the use of rechargeable nickel metal hydride and 12-volt lead-acid batteries that are still used to power the 12-volt circuitry of modern cars today. Tesla was one of the first to start using the more energy-dense lithium-ion batteries back in 2008. These early battery packs were composed of thousands of small 3.7-volt cells wired in series and parallel to provide the voltage required to run their high-voltage motors. Individual battery cells all have a capacity that is rated in amp-hours or milliamp hours, which is just 1/1000th of an amp. For those not versed in electrical units, you can think of the amp as a volume of electrical current that is stored in a battery, and voltage is the available pressure or force with which that current can be delivered. You'll see markings on most batteries that show the capacity of a battery in amp or milliamp hours. This basically means how much current can be delivered for 1 hour at whatever the battery voltage is. As for the voltage, this is entirely dependent on the chemistry that's used to create the battery. Those lead-acid batteries we mentioned earlier produce just over 2 volts per cell. If you look closely at any 12-volt car battery, you'll see that it's composed of 6 cells that are wired in series to give you 12 volts. Comparatively, lithium chemistry batteries will typically range from 3.6 volts to 4.2 volts when fully charged. There are plenty of exceptions, such as non-rechargeable lithium manganese dioxide batteries that are commonly sold as coin cell batteries with a nominal voltage of 3 volts. These are used mostly in small electronic devices like key fobs, watches, and other small devices. You may have seen a lithium-ion battery with a designation of 18650. This number simply indicates its size, 18 millimeters in diameter and 65 millimeters tall. Compare that with a CR2032 coin cell battery that is 20 millimeters in diameter and 3.2 millimeters tall, and those numbers will begin to make sense. If Bob here was an actual battery, it would be a 1500-2500 lithium-ion cell. Many EVs and hybrids have been designed or used pre-assembled modules where individual cells are packaged together into more manageable blocks. Tesla, for example, has used packs of cells wired up to create modules providing around 25 volts, which are then wired in series again to provide the 350 to 400 volt packs that are needed to drive the motors. We originally considered using that type of battery module that could have been recycled from an older wrecked Tesla, like the Model S, 3, X, or Y, but this idea was not as sexy as it sounds. The battery modules in these cars, much like the earlier Roadster, use thousands of smaller cells that can be difficult to keep track of, especially when using older modules with batteries that have already had some time in service. One of the key factors in providing reliable electrical power for the electronics, as well as the motor for an EV, is ensuring that every single cell in the pack is within the same voltage range. If one cell fails, it can adversely affect the others, but modern lithium-ion batteries are built by machines to tight tolerances that give most packs well over 15 years of life before any significant degradation becomes an issue. Of all the lithium battery chemistries out there, lithium-ion, also known as NMCs, contain nickel, manganese, and cobalt. Although widespread and used in so many of our devices today, they have come under some scrutiny, primarily due to the high environmental and social costs associated with raw material extraction, along with energy-intensive manufacturing. However, with the ever-increasing development of more environmentally responsible manufacturing, we think we found a better solution for our batteries. LFPs, or lithium iron phosphate batteries, appear to be a better choice for multiple reasons. They've already been adopted in EVs made by Tesla, Ford, Rivian, and GM, to mention a few. They're not quite as energy dense as lithium ions, meaning that you get less energy per kilogram of weight, but they do have notable advantages that have helped make our choice. Most notably, they don't use cobalt, a mineral heavily linked to human rights abuses and child labor in the Democratic Republic of Congo. They use iron and phosphate, which are far more plentiful in the Earth's crust than nickel or cobalt, leading to more stable and less destructive supply chains. LFP chemistries are non-toxic and don't leak harmful heavy metals into the environment during disposal or accidental damage, and while they have a lower material resale value than NMC due to the lack of expensive nickel, they are easier and safer to process during recycling. The risk of thermal runaway and battery fires, although very rare, is also significantly reduced with this type of battery chemistry. As far as rechargeability goes, they are far superior to lithium-ion with recharging cycles that outperform NMCs by double in some cases by thousands of cycles. At first, we considered using one of these pre-built battery modules that have a pack voltage of just over 200 volts. We would need at least 2 of them to get the required voltage for a motor, but we'd also need to double that up to get the capacity for our range targets. Although these packs have built-in cooling and connectors for easier installation, the price and availability of these packs was a big issue for our build. Currently, the search for LFPs has led us to a very specific battery and supplier that can potentially provide us with the amount that we need to power a Tesla motor. But we're going to have to build our own pack from scratch and integrate it into our truck frame. This is the size of one lithium iron phosphate cell that we'll be using from EV batteries. Lithium iron phosphate batteries are constantly improving, and this version has a capacity of 314 amp hours, as well as a lower internal resistance, which improves the overall performance and efficiency of the battery. We'll need about 120 of these for our entire battery pack, which will be distributed across the base of our truck frame. Each battery weighs about 12 pounds, 5.4 kilograms, so the combined weight of these batteries will keep the center of gravity low on the truck, helping with driving stability. All that weight adds up, so we'll be looking at well over 1,600 pounds, or about 10 me's, over the 5 individual modules. Our plan is to divide the batteries into 5 modules of 24 cells and build a battery box for each module that will keep them compressed and feature a liquid cooling system. It will also help with safety when servicing and handling, as each module will have a voltage of around 80 volts. You get more of a shock by sticking a fork in an outlet. Another important consideration is allowing some movement of the mounted packs between each other, as the frame rails of the truck are designed to twist a few degrees to help with stress distribution over the entire frame. The exact position between the frame rails will need to be determined once we start to include the other associated components along with the motor itself, but placing the packs here is the overall best location for our build.
You might wonder what makes a good motor for an EV. Electric motors come in all shapes and sizes, and some are better suited than others depending on the application. You've got your fan, you've got your leaf blower, your electric drill, and the vacuum cleaner. But you know what, let me turn all these things off so that you can hear me a little bit better. All motors have 2 components, the stator that remains stationary and the rotor that spins inside the stator and then spins whatever is connected to the rotor shaft. Magnetic fields, either from permanent magnets inside the rotor or from induced electrical currents, are used to create a chasing effect, which essentially is what makes the motor spin. It really is magnetic magic. For EVs, the choice of motors are typically ones that run on either direct current, DC, or alternating current, AC. However, AC motors are favoured more for their efficiency in power and performance. The type of AC motor commonly used in cars and trucks now are either induction motors, asynchronous permanent magnet motors, or a combination of both. Newer vehicles are leaning towards the latter, but both use alternating current passing through coils or windings to generate or induce magnetic fields within the stator. The stator utilizes a series of these coils that are energized in sequence to create a rotating magnetic field throughout the stator. Because the magnetic fields tend to magnetize nearby metals, they induce magnetic fields in metal bars or rods that make up the rotor, at least in induction type motors. The newer permanent magnet synchronous motors use a combination of an iron core with cleverly placed permanent magnets to help with efficiency and to combat some of the negative issues with unwanted magnetic fields that are generated when rotors spin at higher speeds. With some clever use of timing and current control within these stator coils, you can generate a high-powered variable speed motor strong enough to propel a vehicle. We previously mentioned that we're planning to use a very powerful motor that has been used in some models of Tesla over the years. This motor is called the Large Drive Unit, or LDU. We're planning to get a used one from an old Tesla Model S or X, or possibly even an old Toyota RAV4 or Mercedes-Benz B-Class that also use these units. We are aware that there have been some coolant seal issues with these particular motors, but there is a standard solution to address this issue if needed. As far as how the Large Drive Unit should perform in our pickup, the power and torque will be quite noticeable. Diving a bit deeper into these motors, the large drive units are designed to spin at insanely fast speeds, with RPMs maxing out at around 16,000 to 18,000 RPMs. However, their peak efficiency range is usually around 6,500 to 7,500 RPMs, which equates to about highway speeds 60 to 70 miles an hour. This will be ideal for our conversion, but most of our efficiency losses will come from the weight and aerodynamics of our truck paired with the camper. Without the camper, we'd be looking at around 250 to 280 miles of range, but there are many other variables that will affect real-world performance. These are details that we'll address as we dive deeper into our camper design, but as far as the truck goes, there are still small details that can make a significant impact on our truck efficiency. To help us visualize the placement of the LDU, I used CAD, or Cardboard Aided Design, to create this full-scale mock-up of the large drive unit. The LDU is actually a combination of 3 distinct parts. Like most induction motors for EVs, the motor itself is just one part paired with a gearbox to reduce the high speed of the motor down to a more reasonable gear ratio to drive the wheels. In this case, that gear reduction is about 9.7 to 1. Because of the way the magnetic field is generated inside the motor from the high voltage batteries, high torque is delivered to the wheels at any motor speed. The device that handles delivering that high voltage magnetic field is called the inverter and converts high voltage direct current, DC, from the batteries into a variable frequency alternating current, AC, to drive the induction motor. By modulating this AC frequency and voltage, it controls the motor speed and torque. The inverter also manages the regenerative braking, which by converting AC back into DC to recharge the batteries when the accelerator pedal is released. The strong magnetic field that provided all that power essentially works in reverse to effectively slow the motor down while sending that power back into the batteries. With most conventional pickups, the rear-wheel drive system is accomplished by transferring the rotational drive of the engine to the rear differential using an automatic clutch, gearbox, and a long-form drive shaft. This drive shaft then goes into the differential, which is this thing right here, and then converts that longitudinal rotation into lateral rotation with further gear reduction within the differential itself, which determines the rotational speed of the wheels. Many conversions will typically replace the gasoline engine with an electric motor and essentially just tie it into the original drivetrain. With our conversion, however, we're planning to eliminate the drive system from front to back and have the large drive unit power the rear wheels directly. This will effectively reduce many of the frictional losses in the original setup and assembly and give us a more efficient drive system. Now, the biggest challenge here will be how to swap the rear differential unit with this large drive unit and create a solid mountain cradle. We have seen some versions of this done before, but it's not common. We'll dive more into that challenge in another episode.
So with the 2 main components addressed for converting our truck, we'll need to spend some more time with the design of the camper itself so we can ensure that our truck will handle it with ease and efficiency. As far as the batteries and motor go, we have some battery samples here that we'll be running tests on to determine if they're the best choice for us. Ordering 120 of these batteries will be the highest dollar component in our build, so we're doing our research to find the best source for these batteries.
And although we've essentially picked out the motor that we want to use, finding one that meets our budget and still works reliably will be our next challenge. In the next episode, we'll hopefully have some updates on these 2 components, but we'll also take a deeper dive into the truck body modifications and the design of our camper.
So if you managed to make it through to the end of our rant, don't forget to subscribe to our channel here and on Facebook and Instagram. We're really just starting out, so your subscription will really help to build our channel. And as always, thanks for watching and be excellent to each other.
Luke out.